Hi there. My name is Candelora, and I'm a 22 studying physics and Italian at Dartmouth. And as you can see from all the math on the poster here, I'll be presenting on the physics today. I've spent the past term conducting full-time research on the two-dimensional allotrope of carbon known as graphene. Before 2004, graphene was only theoretically considered since it was believed that the inner atomic bonds would break at room temperature. However, in 2004, graphene was discovered, giving rise to a new class of two-dimensional materials and a new class of physics. Now, why is graphene so interesting? The honeycomb lattice structure of graphene that you see here gives it desirable electronic properties that make it a contender in electronic and spintronic devices. Spintronic devices use electron spin instead of charge to transmit a unit of information, which gives higher processing speeds to computers. I've spent the last term researching and trying to understand these electronic properties from a more theoretical standpoint as opposed to experimental. In solid-state physics, we always start by defining the geometry of the system, which is what I set out to do in the bottom left-hand corner here. The most important thing to look at here are the sublattices A and B, which, when put together, give you this honeycomb lattice structure. After a suitable geometry is determined, we move into looking at the energy of the system by analyzing its Hamiltonian. And a Hamiltonian is just an operator that, when acting on a wave function, tells us the energy of the wave function or the system. In the middle of the page here, I go through an algebraic proof where we only allow for different site hopping, meaning jumping from A to B and from B to A. This proof demonstrates a few interesting things. It shows how the filled blue valence band here and the unoccupied conducting band up here overlap at the Dirac point, making graphene a perfect semi-metal with a high mobility rate. And not only do they overlap, but as you can see here, the energy is linearly dispersed in k momentum space. This means that the charge carriers around the Dirac point behave in a relativistic manner, even though they move at about 2 orders of magnitude slower than the speed of light. Therefore, it's believed that there's some hyperfine interaction or greater physics at work here, which is creating this discrepancy. Furthermore, since the energy is linearly dispersed, the density of states are dependent on the energy. And since the density of states depend on the energy, we can manipulate the spin states of the electrons at the Dirac points with a suitable gate voltage to allow for graphene's application to spintronic devices. Over to the right here, I analyze how the band structure changes when various parameters are manipulated. These diagrams come from Mathematica code written by other people that I give credit to at the top here. The first parameter we change is the hopping parameter. This parameter changes the overall slope of the linear dependence, as you can see here, where it gets steeper with greater t. Therefore, it acts as a sort of gauge or scaling factor to ensure that the theoretical equations match the experimental measurements. And it's believed that the hopping parameter is about 2.8 electron volts, though that's only an approximation. The next parameter we introduce and change is allowing for one type of same-site hopping, meaning now we can jump from A to A or from B to B, but not both. When we allow for this, we introduce a band gap between the valence band and the conducting band, which makes graphene more appealing for logic circuits, since with this band gap, graphene can be turned on and off, whereas without the band gap, graphene can only be on when a current's going through it. And a band structure like this generally comes about when there are some sort of impurities in the material, whether intentional or unintentional. And the last parameter we analyze is allowing for both types of same-site hopping, meaning from A to A and from B to B. If same-site hopping amplitudes are equal, as you can see here, the Fermi level is raised from 0 to whatever that amplitude is, which is effectively what happens when we introduce a suitable gate voltage to pure graphene. And so over the summer and the next year, I hope to expand this research on theory into experimentation to analyze and characterize the charge carriers in graphene devices by using EDMR to see how possible it is to control the spin states of graphene. Thank you for your time, and I hope you have a great day.